The title of my talk is Large-Scale Fault-Tolerant Universal Quantum Computing with Quantum Teleportation. My name is Akira Furusawa from University of Tokyo and Riken. Let me introduce myself. This is a picture of more than 20 years ago. And this is me, looks young. And this is a quick project started at 1996. And a lot of good people were there, like Daniel Gottesman and John Preskill. And in this quick project, I did teleportation experiment. And now we are working on quantum computers. Since this quantum teleportation experiment, I have been working on quantum teleportation for more than 20 years. This Daniel is my God, and his papers are my Bibles. And I'm a crazy windsurfer. These are my collaborators. Here is my group at University of Tokyo and Riken. And here is my senior collaborators, especially these moonshot people. And these days, we have a lot of entity people to make real devices. And special person is Kashiwazaki-san. And our qubit called GKP qubit, that is a logical qubit for error correction. And this type of, and of course, G of GKP is G of Gottesman. And K of GKP is Kitaev, and P is Preskill. And GK, so sort of my colleague. And we encode these GKP qubits by using coherent communication methodology that is called quadrature amplitude modulation, or QAM. That is optical frequency radio. I mean, AM radio and FM radio. Older people like me can understand AM radio and FM radios, but younger people cannot understand these radios. So I have to explain these mechanisms. And AM radio is amplitude modulation like this, and sound is encoded in amplitude. Information is encoded in amplitude like this. And FM radio is like this. Information is encoded in frequency or phase. And QAM is doing radio in optical frequency and use amplitude modulation and also frequency modulation. And these AM signal and FM signal can be regarded as complex amplitude, which correspond to annihilation operators in quantum optics. And in this case, X and P becomes conjugate variables like this. So we have an uncertainty relationship. And also, in that case, we can make superposition of these information. That is logical qubit or GKP qubit. By using this type of GKP qubit, we can make logical operation by using optical communication methodology. For example, if we want to make a bit flip or Pauli X operation, we can just add A modulation by square root pi like this. So just shift this way and switch to 1 like this. Or if we put 90-degree phase rotation, we can switch from 0 to plus or from 1 to minus. Of course, plus means superposition of 0 and 1, plus superposition of 0 and 1, and minus means 0 minus 1. And this type of switch can be realized by using 90-degree phase rotation. And for phase flip or Pauli Z operation, we put frequency modulation or phase modulation. I mean, displacement in this direction by square root pi. We can switch plus to 1 like this, and inverse. These are Clifford operations. And also, for universal Clifford operation, we should have this operation S, 90-degree rotation around the axis, phase gate, from plus to I. I means 0 plus I1. And it can be realized by using optical communication methodology like 45-degree rotation from here to here, and then displacement. I mean, simultaneous modulation of AM and FM, and we can shift from here to here, and then we make squeezing or parametric amplification. Then we can come here. Up to here, we can realize all Clifford operations or Clifford universality. And for universal operation, we need one non-Clifford operation. That is this pi over 8 gate. And for universal, for fault-tolerant quantum computing, we should just use Clifford operations. We should not use non-Clifford operations. So we should synthesize non-Clifford operation by using Clifford operations. That is called gate teleportation. I mean, gate teleportation can be realized only by using Clifford operations. But for make non-Clifford operation, we need non-Clifford ancillary inputs like cubic phase state or a magic state. And by using ancillary input, we make universal operations. That is a story for us. And to realize that fault-tolerant universal quantum computing, we use only these setups. I mean, only 4 OPOs and 5 beam splitters and two delay lines. We can realize ultra large scale operation, say up to 10 to 9 or even more. And so we can make this type of large scale operation only by using 4 POs. That is because we can build a macro node here by using 4 input and then make entanglement one by one in time domain and make spiral like this. And also it is universal. I mean, up to here is just homodyne measurement, but here we make teleportation or by using ancillary input, we can make projection onto non-Clifford state. And also it is fault tolerant because we use GKP qubits. And we are using optical communication methodology. So we can change this homodyne measurement, switch this one to optical parametric amplifiers. So now this one becomes optical parametric amplifiers. In this case, we can make all optical quantum computer with 10 terahertz clock frequency. Now, of course, that is my dream. But important message here is that the clock frequency is much, much faster compared to conventional computers. That means it is really powerful. And in this case, we don't have to have quantum algorithm like Shor's algorithm to make computers fast. So this optical methodology is really powerful. And 30 or even 40 years ago, a lot of people believed that optical computers should be next generation computers because carrier frequency of optical system is more than 100 terahertz. So we can realize 10 terahertz clock frequency. But optical computers disappeared. That was because optical computers were analog computers. So we could not make error correction. But by using quantum mechanics, now we can make error correction. So our quantum computer or optical quantum computer is revival of optical computer, and it can make error correction. So quantum, the word quantum has two meanings. One is, of course, quantum mechanics, but Another means digital or discrete. And I want to explain the methodology of quantum computing. Of course, everybody believes that, everybody knows that quantum circuit, everybody knows this quantum circuit model. These quantum gates make a circuit. That is a circuit model. But in our case, we use a measurement-based model or one-way quantum computing. In this methodology, we use a large-scale entangled state, which is called cluster state. And cluster state is can be regarded as a quantum lookup table. That means a superposition of input-output relationship. And this lookup table is universal. And by using measurement, we can select one of them. That is cluster state. And we make measurement here, and the measurement result is random. And to eliminate the randomness, we make operation depending on the measurement result here. Because these are entangled, this measurement makes some effect here, and we make some operation here. It is a kind of error correction, and we select one calculation from quantum lookup table. And this methodology is pretty much the same as quantum teleportation, one step. And overall, it can be regarded as sequential teleportation. And this methodology is really powerful for flying qubits or traveling wave. If we use a quantum circuit model for flying qubits or photons, it is nightmare because large-scale quantum computing needs large-scale optical setup. And even worse, there is no flexibility of the setup. I mean, in the case of flying qubits, we need real quantum circuit. So if we change the calculation, we have to change the circuit or setup. That is totally different situation from stationary qubits like superconducting qubits or ion traps or spins. In those cases, they don't have to have a real quantum circuit. Quantum circuit is virtual. It is kind of score. So just score or pulse sequences, control pulse sequences. So it is a nightmare for flying qubit to use a quantum circuit. But we can solve all problems by using measurement-based model. For example, we can create ultra-large scale cluster state. And by using by changing the measurement basis, we can make universal operations. And it is teleportation from here to here, and then here to here, and here to here forever. And it is really powerful because we are using traveling wave, and we make measurement within laser coherence time. So we don't have any decoherence. We can do it forever. And this is a picture how to make a cluster state. By using squeeze state, we make bipartite entanglement and then delay by one wave packet and recombine here and weave cluster state and make measurement and feed forward. And this methodology can be extend to two-dimensional, and we can create a large-scale cluster state only by using 4 squeezers and 5 beam splitters and 2 delay lines. Mechanism is like this. First, we create 2 series of bipartite entanglement like this. And then we put a beam splitter here. And we create 4-party entanglement like this. More precisely, we are using wave packet like this. And if we look at, for example, here, that is 4-party entanglement. And then 4-party entanglement, 4-party entanglement, and so on, like this. And we make delay lines. We have delay lines here and here. And this delay line makes this delay correspond to by 1 wave packet. And this case, n equals 5, so delayed by 5 wave packets here. And then we have beam splitters here and here, like this. Then if we look at these 4 wave packets, these 4 should be entangled. I mean, 4-party entanglement, like this. So it looks really messy, but if we arrange this one like this, we can see these macro nodes and 2-dimensional cluster state like this. More precisely, it is spiral. Because we are using only 4 squeezes. So it is just time domain picture. The entanglement can be checked by using so-called Van Lyck-Furusawa criteria. By using these 2 stabilizers or nullifiers, we can check the entanglement or non-classical correlation in these 6 web packets. And similarly, by using these stabilizers or nullifiers, we can check these 6 web packet entanglement or non-classical correlation. And changing the mode index, K is mode index, I mean time domain. So 1, 2, 3, 4, 5, like this, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, like this. We can check these entanglement. And this is a witness of the entanglement. And similarly, by using this 6-part entanglement and checking in time index 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, and check this inequality, we can check whole entanglement. And for this, we need 4.5 dB of squeezing. Of course, this is minimum requirement. And we did that experiment. We prepared 4 squeezers and 5 beam splitters and 2 delay lines. And reality looks really messy. We have 4 squeezers and many mirrors and beam splitters and 2 delay lines. One is free space. Another long delay line is a fiber. And this is the result. We checked 4 non-classical correlations. And below this 4.5 dB level, so we declare the success of creation of 2D cluster state. Now, I will explain these operations. So by using measurement, we can select one operations. And for fault-tolerant quantum computing, Clifford operations are enough. So we try to realize these Clifford operations. That can be realized by changing measurement basis. In this case, 2 homodyne measurements, and we changed local oscillator phase by using phase modulators, EOMs. And this signal generator, we changed local oscillator phase. And we realize phase rotation like this, and shear, that is phase rotation and squeezing, and pure squeezing. These dots correspond to experimental data, and these curves theoretical prediction, and agree with each other very much. So we realize Clifford universality. And now we should try to make non-Clifford operation by using gate teleportation. And we tried this cubic phase gate. Cubic phase gate was proposed again, this GKP people, Gottesman, Kitaev, and Preskill, like this. This is arbitrary input, and this is ancillary input. this is teleportation circuit, Clifford operations, and this qubit phase gate operation is teleport to arbitrary input like this. And in Heisenberg picture, I like Heisenberg picture because we can see input-output relationship like this. So cubic phase gate is this type of nonlinear gate. So by using this one, we can make multiplication. Only Clifford operations, we can just linear operation, but by using cubic phase gate, we can make nonlinear operation like this. And for this, we need cubic phase state. So in Heisenberg picture, it is this type of non-classical correlation. And we try to realize the cubic phase gate and propose this scheme. It looks very complicated. And even for us, it was too complicated. And too complicated means too low fidelity. That is because we use many measurement and feed forward here and here and here and here and many. So we have to cross the boundary between quantum information and classical information, which means a lot of quantum duty. That's why very low fidelity. But fortunately, we solve that problem like this. Here, the setup looks really simple because only 2 ancillary inputs and only 2 beam splitters. But here it looks really nasty. So, but optical setup is really simple. That's why it should be high fidelity. And here is input-output relationship of discrete teleportation. And if we have enough amount of squeezing, we can neglect these terms. And if we have enough amount of cubic phase state quantum correlation, we can neglect this term. So here we can get cubic phase gate operation and 2 dB, 3 dB of squeezing. Of course, optical setup is really simple, but this part looks really nasty because here is homodyne measurement and gets a value of x here. And by using this x, we calculate this arctangent. So this is a calculator. And then by using this theta, we make adaptive homodyne measurement here and get this p theta. And then by using this theta here and this theta here, we make calculation and make displacement. So this part looks really ugly, but optical setup is really simple. And this methodology can be regarded as quantum noise reduction with non-classical states of light. That's for sure. But we have more meaning. One is that optical nonlinearity can be created with classical nonlinear feed-forward. This message is really powerful because this classical nonlinear feed-forward is electrical circuit. So we can realize 100% of fidelity. And of course, it is just classical. To make it quantum, we need non-classically ancillary input. So we can divide the problem into two problems. One is preparation of this nonlinear feed-forward circuit. And another one is ancillary state preparation. And here is projection onto cubic phase state, actually. And we can, by using this methodology, we can realize universal quantum information processing like this. For this, of course, we need cubic phase state. Cubic phase state is like this in Schrödinger picture, and in Heisenberg picture, this type of non-classical correlation. And this is a parabolic function in phase space. And lowest order approximation is superposition of 0 and 1. I mean vacuum and single photon. And we can create this single photon like this. So we have this state. And then we found the methodology of real-time measurement of quadratures, because it is web packet. So we can make quadrature of web packet. That is non-trivial, but we realized that methodology and then made feed-forward. For this, we made this ultra low latency FPGA board. Actually, that is a lookup table, because digital processing has latency, huge latency. So to solve that problem, we made a lookup table. And by using that lookup table, we can make a calculation in 1 clock. And this is experimental data, not simulation. So it is very fast and precise. And to synchronize this electrical signal and optical signal, we made delay line here. That was Heliot cell like this, and this is picture of this mirror. And this is a real setup, really messy, many optical components. And we did detector tomography. So for this, we put various coherent state and did detector tomography. And this is the result. We can see the projection onto a parabolic function. So we can declare the success of projection onto a cubic phase state, which means we have universality of operation. So now we are moving on to another topic, that is these squeezers. Up to here, we used these OPOs, but now we are changing these OPOs to OPAs because it is very broadband. First step, as a first step, Kashiwazaki-san in NTT made this single mode PPLN waveguide and realized 6 dB squeezing with 2.5 terahertz bandwidth. And in that experiment, for squeezing measurement, we made just homodyne measurement. So the bandwidth was not so broad and up to 300 megahertz or so. So we checked the bandwidth by using parametric fluorescence, and it was more than 2 terahertz. And next step, we measured that squeezing directly by using 2 squeezer or PPLN waveguides. One is, of course, a squeezer. Another one was used for optical preamp, parametric amplifier. This is this guy's noise figure is 0 dB, so we can amplify this squeezing, and the signal to noise ratio of this signal determined by this signal to noise ratio, and this optical preamp's signal to noise ratio should be 0 dB in principle. So we can get squeezing. We can measure squeezing by using, for example, optical spectrum analyzer. And we did that experiment. And at that time, the PPLN waveguide has some losses, so it was double because we are using 2 of them. So the squeezing was only 3 dB and bandwidth was 1 terahertz, but this is direct measurement. But now we have 6 dB of squeezing and 6 terahertz bandwidth. That is direct measurement of squeezing. And the paper was accepted in APL, and it appears soon. And next issue is ancillary inputs. For fault-tolerant and universal quantum computing, we need ancillary input like GKP qubit and cubic phase state. And for the creation, we use a deterministic state synthesizer. And it should be a traveling wave for our case. These days, there are some reports that GKP qubit got in a microwave, but they are just standing wave in a cavity. So we cannot use it. This is very important message. And for us, first we create entanglement between inside this cavity and outside the cavity. These are called signal and hydra. And entanglement is like this, N-type entanglement. And hydra go to this generalized measurement, squeeze input, and photon number resolving detectors, and beam split the network. So we make a projection onto a desired state here. Then we can make the desired state here in the memory cavity. And actually, this memory cavity has a shutter. And at the very beginning, it is closed. But after, when we want to use this state, we can open the shutter and we can use this signal. And we did that experiment. We created superposition of 0 and 1, vacuum, and single photon like this. That is lowest order approximation of cubic phase state, and memorized. We have slight phase rotation. That is because slight detuning, but we succeeded in the negativity of the Wigner function and phase information. Important message here is that we can memorize phase information. That's why we can memorize cubic phase state and also GKP qubit arbitrary state. And we are developing photon number resolving detectors. For example, transition edge sensor like this, 1, 2, 3, 4, 5 photons. And recently, we found a new type of photon number resolving detector that is so-called SSPD or superconducting nanowire. Superconducting nanowire is regarded as on-off detector, but we used it as transition point sensor. Here is superconducting state, and here is normal. So usually on-off sensor, photon comes, superconducting state broken, and normal. And this on-off is tells us existence of photon. But if we look at here really carefully, we can see like this. I mean, we can have photon number resolution like this. And we did detector tomography, and we checked it works as photon number resolving detector. And by using this one, and also by using this OPA, we created Schrödinger cat state like this. And here, important thing is it is without any correction. That means we can use it. From this result, we can say that the squeezed vacuum from this OPA is really pure. We can use this squeezed vacuum to use non-Gaussian state like this. And now we have to create GKP qubit. This is one methodology. One unit has 3 squeezers and beam splitters and 2 photon number resolving detectors and 4 units and beam splitters and on-off detectors. We can create GKP qubit, very high fidelity of GKP qubits. And of course, at the moment, it is just heralding scheme, so really conditional scheme. But we will try to combine our memory methodology and this one to make it deterministic. So up to here, I explained this one, all of them. And we can realize large-scale quantum computing only by using 4 POs and 5 beam splitters and only 2 delay lines and several detectors. So we don't have to have a chip. Modules and fiber optics are enough for large-scale quantum computers. That is my message. Everything is in this book. It is coming soon. Thank you for attention.
Thank you very much. Thank you very much for the very exciting, interesting talk. And now the floor is open for question and answers. If you have any questions, please type in the Q&A tab at the bottom of your screen. If you don't, if there's no question at this moment, let me start a question. When do you think that demonstration of the real as a system optical quantum computer, when will it be demonstrated? Will it be very soon, almost there, or maybe years away?
So of course, if your question is for fault tolerance, it is quite a long time. But just Clifford operations in couple of years.
Okay. Thank you very much. Okay, so the question is, Ajay Parikh, how many qubits can you scale this setup?
So in principle, 10 to 9 or even more. It is determined by, let's see. It is determined by coherent length and this delay line, and this delay line, which correspond to size of the wave packet. And it is determined by the bandwidth of this squeezer. And now say bandwidth of this squeezer is 1 terahertz or even 10 terahertz. Time duration is 1 picosecond. And 1 terahertz corresponds to 1 picosecond. And fundamental laser has say 1 kilohertz bandwidth. So 1 millisecond. Of course, just ratio between bandwidth of OPO and fundamental laser wavelengths, fundamental laser. And so 1 terahertz means 10 to 12. And 1 kilohertz means 10 to 3, 10 to the third. So 10 to 9 qubit. We can handle 10 to 9 qubits. So if we use 10 terahertz, 10 to 10, that is our scale.
Okay.
And another point is that we are using logical qubit, not physical qubits. In the case of physical qubits and make error correction, for example, surface code, you need many physical qubits, 10 to say 10 to 5 or something. In that case, you have to care about the number. But in our case, one wave packet is a logical qubit. That is totally different situation. So we don't have to have 10 to 5 qubits for fault tolerance. I should say 10 to 1,000 qubits should be enough.
Okay, thank you very much. There's one question from Robin Dawson. Is it possible to implement these structures on an integrated photonics platform?
So it is a good question. I think it is very hard. That's why we should stick to fiber optics. That is because silicon photonics is really lossy. And there is a trade-off. If you want to have a broadband, you will have a lot of losses. So if your computer is really slow, in that case, you can use silicon photonics or silicon nitride photonics, but I don't think so. That's why our methodology is really powerful, because we only use 4 squeezers. In any case, another system use spatial domain multiplexing. There is no scalability, I think so. But in our case, we are using time domain. that is totally different methodology, and we have a lot of scalability. So very small number of components, and we use it many times in time domain. That is our methodology. That's why we have scalability. But in the case of spatial domain multiplexing, you need a lot of space, right? So I don't think there is scalability, even with integrated circuit.
Okay. Then next question is from anonymous attendee. What kind of laser was used, frequency band, and can you use only that frequency of the laser?
We have to use communication wavelengths. That is because loss of fiber is minimum. So we have to use optical communication wavelengths. There is no other option.
Thank you. So another question is from Ajay Parikh. Very impressive. What are pros and cons of this setup compared to ion traps, superconducting junctions, that is state-of-the-art IonQ quantum computer or D-Wave?
So as I said before, we are using time domain. So it is really scalable. So the other system, if the problem, if the problem to solve is bigger, the setup should be bigger. But in our case, totally different. Always the same. It takes a little bit longer time. That is different. Totally different world. So I don't think we have any weakness.
Okay. Another question is from Dean. Do you have to do anything to synchronize the OPOs?
Of course, we have to use same pump light, same fundamental laser. But these days, very precise frequency standard like optical lattice clock. By using that methodology or technology, we can realize the locking between two remote fundamental lasers. In that case, we can make synchronization between OPOs.
Okay. Any more questions? Another question. How close are you to commercialization?
I don't know. So if you need fault-tolerance, no idea. But in 10 years or something. But if you just want to have a quantum computer like IBM Q, I think within 2-3 years.
Okay. Thank you very much. Any more questions? Okay. If not, let's conclude this session. And we'd like to thank Professor Furusawa very much. Thank you very much.
Thank you.